Hi, this is Professor Lynn. So this is going to be your first pre-lecture video talking about section 1.4 here, which is a more formal view of probability. So you've probably seen lots of the probability stuff that we've talked about before. It's probably pretty familiar. What we're doing in this section is introducing some more formal notation to make this rigorous, and then that'll enable us to do more with this later on. So suppose we've got some sort of random thing happening, like rolling 2 dice, and we'll start by listing the possible outcomes. So in the general notation, that would be with the omega 1 up through omega n. Looking at our specific example here, rolling 2 dice, our outcomes are the first one is 1, the second one is 1, first one is 1, second one is 2. First one is 2, second one is 1, etc. All of the different possibilities that you can have here. So then we take all of those possible outcomes and put them together into a set, capital Omega, and we call that the sample space. So this is the set of all possible outcomes. Then an event is a subset of omega. So for example, we can have an event with just one outcome in it. So this would be the event that both rolls are a 1. We can have an event with a bunch of different outcomes in it. So for this one, this would be, we think about this as being the event that the first roll is a 1. And so these are all of the outcomes that meet that condition. That's our event in that case. We could have this event so we would think about this event as being the sum of the rolls is 4. So we've got our different outcomes that achieve that by having 1 and 3, 3 and 1, 2 and 2. Although usually when we're talking about events, they'll have some sort of condition that we're trying to meet, like we saw in those examples, but really they don't have to follow any kind of pattern. Any subset of the sample space is an event. All right, so now we've got our setup with our sample space. We're going to talk about what a probability actually is. So for each outcome, we assign it a probability. So that's going to be what you would normally think about as the probability, that kind of fraction that's giving how likely that outcome is. So for the outcome 1, 1, the probability of that happening is 1 out of 36, and same thing for the outcome 1, 3, 1 over 36 there. So in this case, all of our outcomes have the same probability because these are fair dice, but that won't always be the case. Sometimes you've got a loaded dice where one thing is more likely. So let's say I've got dice where it's going to land on 1s a little bit more frequently. Maybe I've got like 1/10 here and 1/30 there, something like that. These don't have to be the same for all of the outcomes. They just have some probability. They do have to have the properties that the probability should always be positive or non-negative. So we don't have negative probability. That doesn't really make sense. And once we take all of the outcomes and add up their probabilities, we should get 1. So taking all of the different possibilities, those probabilities should add up to 1. So the result of this is that P gives us a function from the sample space omega to the interval from 0 to 1. So as inputs, we have our outcomes, which were things in the sample space, and as outputs, we have numbers between 0 and 1. And this function is called a probability measure. When we put omega and P together, so the sample space with the probability measure, that's called a probability space. And that's sort of our basic framework for working with probability, is like our starting point is a probability space. So we can, in addition to talking about the probability of outcomes, we can talk about the probability of an event. So for an event E in omega, so remember E is a subset of the sample space. The probability of E, we get that by summing all of the probabilities of outcomes that are in E. So another way to write this would be as P of let's see, I guess there's not a better way to write that. Looking back at our example there, looking at the event where both of them are ones, then the probability of that event would be the probability of the only outcome in there. So we've got 1 over 36 there. For the event that they sum to 4, we've got 3 outcomes there, so we're going to add up their probabilities. So probability of 1, 3 plus probability of 3, 1 plus the probability of 2, 2, and those will add up to 1 over 36 plus 1 over 36 plus 1 over 36. So we're just adding those probabilities together to figure out the probability of that event. Note that if we take the probability of the sample space, so we can take our event to be the entire sample space, so including all outcomes, then we're adding up the probability of all outcomes, so we're going to get 1 there. If we take our event to be the empty set, so that contains no outcomes, then we're not adding anything up, we get 0 there. If E is an event, there is also a related event that's not E, so that's the set theoretic complement EC contained in omega. So here EC equals the set of events in omega which are not in E. So we take outcomes, not events. We take all outcomes which are not in our first event, E. Then when we look at the probability of not E, well, if we know the probability of E, we can figure this out by doing 1 minus the probability of E. So for example, if we're looking at the event that the first roll is a 1, then looking at the event where the first roll is not a 1, so that's going to be the probability of E complement. We can figure that out by doing 1 minus the probability of E, so 1 minus 1/6. We have ways of combining events to get new events. So if we're looking at two events A and B and we want to know what's the probability that A or B happens, we figure that out as the probability of the union of those two sets. The probability that A and B happen, so that they both happen, that'll be the probability of their intersection. So this can be a little bit weird to think about this in terms of the set notation. But looking at this as an example, hopefully we'll clear it up a bit. So if A is the event that the first roll is a 1, and B is the event that the sum of the rolls is 4, so we're looking at these two sets written out here, then the probability of A or B, so that's the probability of the union, then we're looking at the probability of the event that we get, or the event that we get by taking all of those outcomes together. So we've got 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. We've already got 1, 3 listed, and we're adding on 3, 1, and 2, 2. So we figure that out by taking the union, and when you think about this as a set, well, we've listed everything where the first roll is a 1 or the sum of the rolls is a 4. So this is inclusive OR, so having them both happen, that's okay. So 1, 3 is included in that union. For both of them happening, when we're looking at the probability that A and B both happen, then we're looking at the intersection. So then we want to look at the overlap between those sets. So we'd figure that out as the probability of 1, 3, since that's the only overlap between those two. You'd figure that out by finding that probability. In the case where there's no overlap between the two events, we say that they're mutually exclusive or disjoint. So that happens if their intersection is the empty set, so they've got no common outcomes between them. So for example, if A is the first roll is 4 and B is the sum of the rolls is 4, well, those can't ever both happen at the same time. So when we're looking at the set A written out here and the set B written out there, we see that there's no overlap between those sets. So their intersection is the empty set, and we would say that those are mutually exclusive or disjoint. In the case where we have mutually exclusive or disjoint events, then we can compute their probability of the union really easily as P of A plus P of B. So if we're looking at the union of these two, we'd do P of A plus P of B. So the probability of A happening, that's 6 out of 36, plus the probability of B happening is 3 out of 36. So you need to be careful about this, that you're not doing this in general. So this is specifically for mutually exclusive events. If they're not mutually exclusive, so they have some outcome in common, then what you'll end up doing is double counting that outcome, and your probability will be higher than it should be. So make sure you're only using this for mutually exclusive events. Now, so once again, we've got our framework with a sample space omega and probability measure p giving us our probability space. A and B are events. Let's suppose the probability of A is bigger than 0. So we've got something that will sometimes happen at least. Then we define the conditional probability of B given that A occurs. That's denoted by, we write that P of B bar A, and we compute that by doing the intersection, probability of the intersection of A and B divided by the probability of A. So what we're looking at here is thinking about this. If we know that A occurs, then what's the probability that B occurs? So we've got some additional information than more than what we'd usually have looking at this probability space. We know that A is occurring. Now taking that as like our total possibilities, then what's the probability that B occurs? So for example, looking at these two sets, A and B, so here A is the event where the sum of the rolls is 4, B is the event where the first roll is a 1. Then when we're looking at the probability of B given A, that's the probability that the first roll is 1 if their sum is 4. So we're looking at if we know that the sum is 4, then what's the probability that a first roll is 1? So sometimes you can kind of figure this out without using this formula. So if we're looking, well, we know that A happens, so we know one of these guys is happening. And inside of there, what's the probability that the first roll is 1? Since these are all, equally likely things, we can kind of work out that it's going to be 1/3 there. But in general, that might not be possible in all cases to kind of reason that out. So you might want to compute that as the probability of A intersect B over the probability of A. And then the probability of A intersect B. So A intersect B is just 1/3. That's the only overlap there. And the probability of A is 3 over 36. So looking at the probability of just that event 1, 3, that's 1 over 36. And so this works out to be 1/3, like we kind of reasoned out, but we can do that with that formula as well. So another way that two events can be related to each other, we say they're independent if the probability of B equals the probability of B given A. So this means that knowing A happens doesn't affect the probability that B happens. So for example, if we're rolling 2 dice, then the roll for the first one shouldn't affect the roll for the second one. So those would be independent events. Each die roll, or independent trials. There, so those are independent things happening. For independent events, the probability that A and B both happen, that's the probability of A times the probability of B. So you can figure that out that way. This is something you've probably done a lot in probability. So if we're rolling, 2 dice and we want to figure out the probability that we get a 1 and a 1, for example, we do 1/6 times 1/6. So this is something that's very familiar there. All right, so that's our new formal notation for probability. So we're going to be doing more with this in the next few sections. So make sure you get comfortable with this notation, understand all of the turns, and make sure you submit your answers to those pre-lecture questions. As usual, feel free to email me if you have any questions. If anything is not clear, it's better to get those things cleared up as soon as possible. So feel free to send me an email. All right, that's it for this one.